Wu. Dr. Wu was a specialist geotechnical engineer at BC Hydro with about 30 years of practicing experience. He has been heavily involved in design for seismic upgrade projects that include BC Hydro's John Hart Dam, Ruskin Dam, and Metro Vancouver's assessment for the first Narrows and Port Mann water supply crossings in 2000, as well as TransLink's analysis of the Pattullo Bridge, construction of the SkyTrain infrastructure for the Millennium Lines and Canada Lines. And Dr. Wu has over 50 publications to his name in a variety of seismic and liquefaction studies here. And he's been a fixture at the VGS for some time. He's given presentations in 2017 and 2018 on the probabilistic approach to seismic design of structures for both crustal and subduction earthquake sources. So put your hands together and please welcome Dr. Wu.
Hello.
Can
you hear me?
Yep,
Hi, Shane.
Yep, you're online, Guoxi.
Okay, thank you, Shane, for the introduction. My topic is reliability-based dynamic analysis for seismic design optimization in British Columbia.
Oh, I'm sorry, Dr. Wu, just a small interjection. Your video is rotated sideways in the moment here. Can you maybe spin your camera around? There we go.
Is that better?
Yes, yeah, from my end. Thank you.
Okay, so in the last few years, I have presented a couple of times on this Psta analysis, which is probability seismic performance analysis. So I call that Psta. And the first presentation I made was in November 2017, where I did this GSC seismic hazard data review, and then proposed a method to extrapolate the seismic data from the GSC database to 1 in 5,000 year event. And then in that 2017, I also presented one-dimensional seismic site response analysis using this Roberts Bank port profile and the VS measurement from GSC. And later in 2017 or 2018, this VGS Symposium, I also made a similar presentation on this Psta method, but using that for seismic design of upgrade. So in there, I also talk about open-quake method to derive 1 in 5,000 year spectrum, also using the GSC model. So this study I'm presenting today is a continuation of the Psta method. In addition to that, I also tried, or as a first part of the work, try this reliability-based analysis. Next slide, please. Can you move to next slide? Thank you. So in British Columbia, we're in a very special zone with two distinguished earthquake sources. One is the subduction, cascading subduction earthquake, and the other one is the crustal, which is a shallow crustal earthquake. So back one slide, number 2, please. If you can go back one slide to number 2, please. Yes, thank you. Yeah, this one. So the Pacific plate, earthquake plate, is subducting the North American plate. So that is the big event called the subducting interface event with a magnitude of 9. And the other one is the much smaller earthquake with M7 with crustal and subduction interplate. And the difference between M9 and M7 earthquakes is the M9 interface earthquake could generate 1,000 times more energy than the M7 earthquake. Next one, please.
I'm sorry to interject, Dr. Wu. Would you mind closing the Chime video stream and open up the Zoom video?
Okay, thank you.
Yeah. There's a slight delay between when Encore flips the page and then when you see it on Chime, and that's resulting in a 10-second lag or so.
Okay, I think that's what it is.
Thank you. Sorry for all the interruptions here.
Outline of this presentation I have laid out is 3 items. First one, I will very briefly show the GSC seismic data. And second, I will do a seismic response and liquefaction analysis for the soil profile, which is a continuation of the 2017 work. And this last part of the presentation will be reliability-based soil liquefaction analysis, which is a new item which I'm trying today. Next slide, please. Okay. So GSC 2015 fifth generation seismic hazard model. This is the designated model to be used in NBCC 2015. And it's the first model that incorporates this subduction cascading earthquake in a probability model. And in this model, it actually output digital results in a grade of 10 kilometers by 10 kilometers. If you look at this map, those red dots are the output points for the lower mainland. As you see here, there are 16 points in the lower mainland in the map I shown, which is majority of the lower mainland. And the larger star showing the location of Robb's Bank port, which is where the GSC borehole FD95S1 is drilled. So this is the location which I'm going to present the study for study response analysis. Next slide, please. Thank you. So this is there are 2 figures in here. The left one is the direct output from the GSC model, and it shows the one in 2475 year spectrum, direct printout from the GSC database. And you see 3 figures or 3 lines. The red one is what I call that the combined all-source response spectrum, including all interface and crustal, meaning it includes the M7 and M9 earthquakes. And the blue one is just the crustal plus the intricate slab, which is M7. And the green one is the M9 interface subduction earthquake. That is on the left figure. And when we do the design, a question is, how do you use this plot for design of 1 in 2475 earthquake? Do you want to use the green by itself, 1 in 2475 for M9? Or do you want to use the blue, or you use the red for both? So that is a dilemma which faced by the geotech engineer. So the method I have proposed and also presented a couple of times. If you look at the right figure, in that PSPA method, which is the probability seismic performance analysis method, it will require not just 1 in 2475 spectrum, it will also require this 1 in 5,000 year spectrum for each of the M9 and the M7 earthquake source. In 2017, I present this method using the extrapolation, which is shown in dashed line on the right figure. So meaning just extrapolator, you don't need to use this open quick to derive this 1 in 5,000 year earthquake spectrum. And in 2018, I presented the method using the open quick, which is a software that you can incorporate GSC 2015 size model into the open quick, and you can actually compute the spectrum for 1 in 5,000 year for each of the M7 and M9 earthquakes. That is shown on the dash on the solid line in blue and green. So both blue and green on the right figures are the 1 in 5,000 year spectrum. The blue is for M7, which is smaller earthquake, and the green is for M9 earthquake. And for comparison, I have also shown the red, which is the combined 2475 spectrum. So in this presentation, I'm going to show you that using the blue 1 in 5,000 and using the green 1 in 5,000 spectrum in the lower mainland will be as close as you could get to simulate this response for 1 in 2475 from our source by using this PSPA method. Next slide, please. In doing that, I'm going to use this using two examples. The first one is shown in this slide, which is the seismic displacement for slope, and using this simplified or empirical equations by Bryce, which I think most of the seismic geotech engineer are familiar with. So there's two types of equation, which one is 2017 equation for the subduction interface earthquake. That is meant for the M9 interface earthquake. And for the M7 crustal earthquake, in the original equation, we had the 2007 version, but now Brian and Macedo has updated that to 2019. So this is the second equation. And each of the equation is applicable to only one type of earthquake. One is interface, the other one is non-interface. So when you do the seismic PSPA method, you basically actually take the same displacement from the two equations and find the probability for each of the south zone. And then you add the probability at that same displacement to get the probability for the combined M7 and M9 earthquake, which is shown in the last three lines. And then if you are looking for 1 in 2475 year displacement, then your probability level is 1 in 2475 year, which is 0.0044. Next one, please. Now here is how you would do that using this PSPA method. So first of all, you derive a complete curve using the crustal earthquake equation by Breyer. So you will derive this line, the blue line in the figure. So the blue line in the figure is using the 2019 crustal displacement equation by Breyer, and you apply the spectrum at different level. For instance, you apply the spectrum value or spectral values at 2475, level, you get 1 point. And then you apply the spectral acceleration level at 5,000 years, you get another point, which is that in the circle, blue circle, that is the point you will get for 1 in 5,000 year earthquake for crustal and basically for non-interface. By doing the same, using another equation from Breyer 2017 for the interface M9 earthquake, so you do the green curve, which also in the figure. So when you apply the spectral acceleration for 1 in 5,000 interface spectral accelerations, you get the point in green circle. So by doing the same thing, but using spectral accelerations for 2475 years, you get another curve or another point. By doing that continuously, you will get a curve. So you will have 2 curves. One is blue, the other one is green. That is, it is applicable to each specific curve. So you cannot use the combined UHS to either one of the equations, but you could apply the source-specific M7 and M9 equation to each of the curve. Now the question is, how are you going to get the displacement curve or hazard curve for the combined source? So going back to the previous slide, you will know, take the same displacement. At the same displacement between the green and blue curve, if you look at that dashed vertical line, that is how you do that. Take the same displacement, meaning you're going vertically, and then add the probability for each of the source. At that dashed line, you will see the probability for the crustal is the same as the probability for the interface green curve. So you add the two, you will get the combined probability is 1 in 1760 years or 1 in 1760 years event. So that is how you get 1 point. By doing the same, you will derive a complete curve for the red. So now you have the red curve. How do you get the displacement for the combined 2475? Now you go horizontally using the red circle, go horizontally. So that is how you get that 2475 for the red, and then you write down the displacement. So that is the procedure you would go for this PSTA method. Next slide, please. Now, for Vancouver site, so you will see the two curves overlapped at 1 in 5,000 years. The green and the blue overlapped, meaning at 1 in 5,000 years, the displacement from the M7 and the displacement from the M9, which is interface subtraction, are equal. And then in that, you add the two, 1 in 5,000 year event, you get the displacement for 2475, which is double of the probability of 1 in 5,000 year. This is just a coincidence. So it just happened. They are the same using the updated 2019 Breyer's equation. If you're using the old equation, they don't. So this is just to show you, in order to get the combined displacement for 2475 years, you need to use the individual displacement at 1 in 5,000 years. So this actually is the basis for my next recommendations. Next slide, please. Now, I'm going to move to a second topic, which is a second example for this PSTA method, is to analyze the liquefaction for the site response at the rubber bank, which I use this elastic base model, and by using VERSET. VERSET is a dynamic computation finite element program, and it has a one-dimensional and a two-dimensional version, and it has the elastic base and rigid base options. So in this application, I'm using the rigid base, elastic base with viscous base boundaries. And this is just an extrapolation from the user's manual or technical manual from the program. So just to show you, one, you should actually use this elastic base. So the essence is when the surface outcrop motion on the right side would be quite different from the within motion in the middle, meaning underneath the overburdened soils. So if the base is not like very hard rock or very, so basically the base effect is quite significant. This is quite it will require some time to explain, so I will just skip this. Go next one, please. So this one just showing you the comparison between shake and the Versa result, which I basically did that when I was working on a project in Bridge River in BC. So for this one, we basically did Versa analysis, and we did also shake analysis using this, both are using elastic-based theory or model. So the base has a shiver velocity of 450 meters per second, and the shaking level is intermediate with an outcrop PGA of 0.14 G. And the spectrum is showing on the right figure. So the outcrop spectrum is in blue. So you can see after the analysis, you found the within ground motion spectrum is in green. So they're quite smaller than the outcrop motions in this case. And the red is shown in the amplified surface motion at the top of the overburden. And the solid is from shake, and the dash is from Versa. So in red comparison and in green comparison, they matches very well by using the same input motion in blue. Next slide, please. So in this second example for Psta method, I'm going to continue using the 2017 model, which I presented in VGS seminar. So the left figure showing the location of this drill hole that was done by GSC, drilled as a part of the earthquake hazard study. And it drilled into 150 meters depth and with a measurement of shiver velocities all along. So I thought that would be a good site to do the study on the Psta method and also on the effect of elastic base on ground motions. The right figure showing the actual shiver velocity profile used in the Versa dynamic analysis, which is site response analysis, and the red is actually measured. So, and the base is sitting at 114 meters below the surface with an elastic base shiver velocity of 450 meters per second. Next slide, please. So this is the model which I used in the Versa dynamic analysis. It has 114 soil elements. So with 114 meters deposit is 1 meters per element, but it's divided into 13 zones. So we distinguish different parameters using the velocity shown in the previous slide. Next slide, please. Thank you. So the next one just showing the time histories of the shear stress computed from the Versa analysis. So the top figure showing the time histories from interest lab earthquake, the 1965 Puget Sound earthquake, and the lower figure just showing the time history of shear stresses from 1989 Loma Prieta earthquake. So next one, please. By using the time history of the shear stress computed from Versa, then you go through this converting the non-uniform cycle stresses into the uniform cycle shear stresses, and then apply this simplified procedure for factor of safety against liquefaction. So you will be able to compute factor of safety against the liquefaction for each individual input of earthquake ground motions. So this slide, I just show you the result from this analysis for factor of safety against liquefaction for the entire, for the top 30 meters. Again, the blue one is if you apply the 1 in 2475 year ground motions from the M7, which is non-interface earthquake, and the green one, the green dash, showing you the factor of safeties if you use 1 in 2475 year spectrum and match the time histories for the M9 interface earthquake. I'm talking about individual spectrum for M7 and individual spectrum for M9, both for 2475 year earthquake. If you remember the previous slide, on the left one, I showed you the GSC spectrum. They are the 2475 for each of those. So I basically use those two and derive the factor of safety against liquefaction for those two events. Now, what is the, actually, if you do a design, you cannot just consider one source of M7 or M9. So you have to know what is the liquefaction factor safeties for the site, which is shown in red. So the red is the one which you use the Psta method, probability seismic performance analysis method, to combine the liquefaction hazard curve from the two sources. In that one, you actually also need 1 in 5,000 year earthquake spectrum and derive a similar curve for each of the two sources. And if needed, you actually need more. So by doing that, you get this red curve. So the difference is the red curve has a lot lower factor of safeties than both the green and blue. So meaning if you use each individual blue or green, you will underestimate, very unconservative in your design. Next slide, please. Now, another approach is I'm not using 1 in 2475 for each individual, but I'm using 1 in 5,000 years spectrum and develop the time histories for each individual source, and then obtain the factor of safety for each individual source, and then compares that with my red square, which is 2475 for all sources. So you will see the blue and green are on either side of the red, which is similar to the displacement curve from Breyer, meaning if you actually close the two curves, you will actually overlap with the red. For when I did the Breyer's method, it just happened in Vancouver, the green and the blue overlapped at that particular point. But most of the time they don't. They sit on either side of the red curve. So the idea is you want to converge the blue and green into the red. So that is the objective of this PSPA method. Next slide, please. So in this PSPA method, I did 2017. I also present a comparison between the mean value and the average between each of this event. So this is just for information. So if you have time, you can go through those slides. Next one, please. How am I doing on time? So the PSPA, so I'm going to just go through a summary result or summary slide, which I consider this as a very important slide for this presentation, is this PSPA method for displacement calculation and for factor of safety against liquefaction. In the previous two examples, I have shown you how you apply the PSPA method in deriving the combined 1 in 2475 or 2% in 50 years result. So in essence, you're looking for the probability at 1 in 2475 for combined M7 and M9, which is the left square. And there's three distinguished different scenarios. One is top one. The P probability of the combined one could be just equal to the P probability of the M7 in the places where there's no contribution from the M9, meaning if you are very far away from the cascading subduction zone, such as in Calgary, just for example. So in that scenario, the two are equal. So they're equal to P probability at M7. And in second scenario, which is the middle, is where you are very close to the subduction zone, cascading subduction zone, such as you are in somewhere outside of the Vancouver Island, where the subduction actually is dominating. So their contribution from M7 is 0. So in that event, you have the combined one equal to the PM9. But in the lower mainland, we are in the third category, which is the P combined M9 and M7 should be equal to P probability from the M7 plus the probability from the M9, which is in the displacement case from Breyer, it just happens the two are equal, which leads to, for the 2475-year event, for the top case, the 2475 of the combined one would be equal to the 2475 of the crystal or non-interface. In the middle one, the combined one would be equal to the 2475 from the interface M9 event. But for the lower mainland, you're looking to approximately equal, maybe in the 40 to 60% range, depending on the quantity of the response you're evaluating. So in summary, the bottom square showing you method is in the lower mainland, 1 is not equal to 1 plus 1, meaning you cannot use individual probability for 2475 and replace the combined one. Instead, you have to use 1 equal to 0.5 from the non-interface plus 0.5 from the interface M9 event. That means 1 in 2475 year probability is equal, you should use 1 in 5,000 year for each of the subduction interface and 1 in 5,000 years for the non-interface. So that is the first part of my presentation. Next slide, please.
And a quick note, Dr. Wu, you're at about approximately 30 minutes. There's approximately...
How many minutes?
You're at 30 minutes right now.
Okay, thank you.
Yeah, there's approximately 10 minutes left for
so the next topic is on the reliability of soil against liquefaction. So that is a new area which I'm studying, which is associated with the study of uncertainties in earthquake ground motions and also in soil parameters. So in terms of earthquake ground motions, we all know there are a lot of uncertainties. I mean, how many records you're using? 3, 5, 9, 11, 21, or you can use, like Bryce is using thousands of earthquake records in doing his study. The second is soil parameters. You have uncertainties in SPT broke count, liquefaction resistance, and also you have uncertainties in residual strength. So all those contribute to this uncertainties in the study. And by applying this called reliability method of analysis, you're trying to take into the uncertainty into consideration and in doing the risk analysis for hydroelectrical dams or facilities. So there are two major categories in the reliability analysis. The first one is I call it sampling method or Monte Carlo simulations. And that will require a lot of samples, 10 in power 6. In this study, I have used 3,465 samples in method A, sampling method. The other method is called sampling, the approximate method. FORM, first order reliability method, which you will see a lot of application by Dr. Forsky or Professor Forsky from UBC Civil Engineering. So I have done a little bit of summary of the two methods. And the sampling method, basically you are trying each samples and look at which one fails and which one doesn't, and divide the NF by N, so you will get the probability of failure. So continue on next slide, please. So sampling method, you will be able to calculate the reliability index beta, and also in this scenario, I have used 3,465 samples. And in the method B, which is the first order reliability method, basically is more like a closed form solution. And you characterize each stochastic variables by known distributions, such as normal distribution, Poisson's distribution. And then you, by doing the approximate method, you find the reliability index first, and then applying the equation of reliability using the standard normal distribution function, you will get the probability of failure. Next slide, please. Now, what I did here is I used the same soil column, which I used for Robsbank port profile, 140 meters depth, but I'm concentrating on this red zone, which is from the 4 meter to 12 meter depth. And by assume different distribution of the N160, I will compute the reliability or the probability of liquefactions for a select depth, just to demonstrate the method and how you would do it. So in method B, so basically FORM method, so you are looking at performance function, which is G. G is equal to capacity minus the load. So in this scenario, the capacity is cyclic resistance ratio, and the load is cyclic shear stresses induced by earthquake. Next slide, please. So in terms of the reliability analysis, the performance function, I'm looking at the load side first, which is earthquake, ground motions. So in here, as you recall, when you convert shear stress, non-uniform shear stress cycles into this normalized shear stress cycles, you need the magnitude correction, which is in Aegis and Belanger, they call magnitude scaling factor, or I call that normalized cyclic stress, the alpha factor on the left. So the right are the three curves I have incorporated in this reliability or probability analysis. It represents three different scenarios in uncertainties. Next slide. So the top one is a comparison of the B for the three curves, and with the alpha, which I used inverse set, and they are equivalent. They are basically same thing, but different formulations. And the bottom one is I use in this probability study, I used 21 earthquake and equally. So the weight for each of the 21 record are the same. But in the alpha factor on the top table, I have used three slightly different weight, which is 0.3 weight for sitting, and 0.4 for Aegis, and 0.3 for Aegis and seat. But in the 21 record, I have used the same weight. So the weight are equal, meaning 1 divided by 21. So combine the three scenario times 21, you will get 63 cases for the load. Next slide. Thank you. So the next slide is showing the table, the metadata for each of the 21 records. And in this study, I only look at the 1 in 5,000 non-interface only. And as I mentioned, this is a part of the study, which I haven't really completed. And 1 in 5,000 non-interface spectrum. Next one, please. So as I mentioned, so the 63 combination of the record and the alpha factor or the earthquake magnetic factor, you will get 63 result for at each element. So the result I plot here is for element 12, which is at the depth of 11.5 meters. So on the left figure showing you the 63 points, the circle is for the Seaton's equation for Km factor, and the line is the aegis, and the triangle is seat and aegis. So the most conservative one, or most of the time, the alpha of 2 Seaton's equation give you the higher demand. They are plotted in circle, and the line is more or less on average. The right figure showing you the average of the 3 curves for each of the 21 record of the cyclic stress ratio, then that becomes 21 points. And I sorted them, so from lower to high. And the high demand is from the CPE record, and I believe is for San Fernando earthquake. And the lowest demand is from the LA dam, from LA dam record. So you can see the record response are not so spiced, but the CPE is demanding the highest. Next one, please. Now, when you plot those 63 points in a distribution curve, which I call the accumulated probability distribution fraction, which is CDF, if you plot them all and sort them from lower to high, so and then you will see the distribution actually compares to the normal distribution where. So the line is from a normal distribution, and the point or the circle are from the actual sampling of the 63 points. Next one, please. So that is from the seismic demand. Now, if you look at the capacity side, then you will see the N160. I also look at the variation of N160 from 1920 all the way to 29. So N160 varies from 19 to 29 at one increment. And then with assigned normal distribution weight to each of the N160 and plot them on the figure, you will see this is an assumed case using a normal distribution, which is more idealized. You can use this for the method B form, the Dr. Forsky's method. You can use this normal distribution. Next slide, please. So on the capacity side, I have shown you 10 numbers, actually 11 numbers for the N160. And then I will show you also the variation between N160 and the cyclic resistance ratio is on the right figure. So that is from the Seaton's 2004. So you can see that there's 5 curves, right? So they are not like, okay, they all liquefy at the same curve. They don't. So 95% of them will liquefy if the N160 is less than showing on the line. At the bottom curve showing this 5%, which they only liquefy is the N160 is less than that curve. So there's a distribution. So in that case, I have characterized these 5 curves by applying the probability weight according to Seaton. So that is a comparison in the left figure. So the comparison between the circle from the sampling or Seaton's method and with the normal distribution in red. Next slide, please. So by applying the same method of probability analysis for the capacity, so basically you have 11 points for N160 and then you have 5 points for the M160 evaluation with CRR, then you get 55 points. So the 55 points is plotted in circle, right? And then try to simulate that using the normal distribution, and the closest curve is in line with a normal distribution at mean of 0.24 and the standard deviation of 0.066. So just remember, the circles will be used in method A for sampling method, which is you go by sample each of the point. And the line will be used in method B, the form method by Dr. Foskey. So this is just for comparison and to basically to verify the basic A and B method are applicable for the study I'm making. Next slide, please. So now you have done this comparison, derivation of the probability distribution fractions for each of the load and capacity. And now if you plot the probability density fraction, which is different from the probability distribution function. So the PDF for the load, which is shown in blue, and the PDF for the capacity, which is shown in orange. So the blue is CSR, which is cyclic stress ratio, and the orange is CRR, cyclic resistance ratio. And you can see the cyclic resistance ratio has a wide distribution, meaning it has most uncertainties for the N160 distribution, I assumed. But for the time history or for the SQL record, I used the load side, which is cyclic resistance, shear stress ratio is more concentrated, meaning it's less scattered compared to the CRR. And this is typical in the probability analysis. And you apply those two curves in the method B, you will get the reliability index. Next slide. So here is the equation for reliability index, beta, and it requires the four input, the mean and the standard deviation for the load, and the mean and standard deviation for the capacity. Using the curves presented in previous slides, you will get the beta is equal to 1.023 or 26, and the probability of liquefaction is 0.152. Next slide. Now, that is from the probability method B form. And then if you use the method A, which is by sampling, meaning you're using those points, circles in the previous figures, and combine all those circles together, meaning you have the 55 from the capacity and 63 times from the load, and times 55 times 63, you will get 3,465 points for this analysis. And then if you plot all the 3,465 points into this fragility curve for liquefaction factor safety, that is the goal in order to get the probability of failure using method A by samplings, which is shown in the figure in the table. So in the table, you will see the probability of failure from the sampling method is 0.157 at the depth of 11.5 meters. So probability of liquefaction is defined by a factor of safety of less than 1. So if you look at the left figure, so if you take a factor of safety of 1 and go up, intersect with the two curves, you will get the PF for each of the two steps. Next slide, please.
Hi, Guoxi. Sorry to interject. Would you mind wrapping up the presentation in a few minutes here? We're a few minutes over time.
Okay. So I will finish that in 5 minutes.
Okay, all right, thank you. Yeah, and we probably won't have time for Q&A here.
Okay. So I will go quick, and so this slide is just mainly for information, how to compute the VS30s for from the VS30 distributions. So that's the table on the right up. And then the comparison between the class F and class E. And next slide. So in this slide, just to show you why the site for class F has de-amplified the ground motion by that much. So basically you have outcrop ground motion of 0.5 to 3G. After you do that, you get the within at the base, you get 0.31G. And then you amplify, you transmit that to a relatively soft deposit, you get 0.2G at the surface. So the 0.2G is from the class F. But if you apply the class E using the Coates method and BCC method, you will get 0.38G. So next slide. So this one just showing you the comparison of the input at the outcrop and the output at the surface of the deposit. The blue is input and on the right figure, and the dashed black is output. The next slide. So really, this is just a comparison between method A and method B for the reliability analysis. So from method A, using sampling method, you get a probability of failure of 0.157. And if you use method B in form, you get a probability of liquefaction of 0.152. So they are very close. So that is the confirmation of verification I kind of want to do just to make sure they are aligned. And if you compare that with the deterministic method using the center value of N160 of 24, the factor of safety between the two methods are not that much off. So meaning they are in line at the mean. Next slide. Now, since we have done the verification for the normal distribution, so the idea is, okay, if I don't get a normal distribution for N160, what happens? So this is another site or another assumption for the B set of the N160 with the N160 from 19 to 29, but with different variation in red in the figure. So you can see this figure showing you is not normal distribution, it's biased towards N160 of 22, you get a probability of 37 at that point. And normally you would apply that N160 of 22 in the analysis when you do a deterministic analysis. Next slide. But what if you apply this probability analysis method and using this biased N160 distribution and compare that with normal distribution result? That is the comparison shown in the figure. So the normal distribution is in the dashed line, the lower one, and the solid one is the biased one. So there's the impact is between a factor of safety of 1 to 2. So there's a major impact, not major, but there's a larger impact in the middle. And next slide. But in terms of factor of safety, they're not that much different in terms of probability of failure. So now for this bias, the set B N160, now if you actually turn on this polar pressure in the analysis, meaning you are doing a effective stress analysis, and in that case, you will not have you will have a COV of not zero, meaning the load and the capacity are inter-affected. So in this scenario, you will require to run the 465 runs in Versat. Basically, I did 3,465 runs in Versat and compute the curve in green. So that is the figure on the left. The green is the result from the effective stress analysis. As you can see, the effect is not in the middle, but in the lower part. So with a factor of safety of 1, there's a major effect on the probability of liquefaction by using the effective stress analysis. Next slide, please. So I will have just 2 slides to go over. So this next slide is quite a complicated slide. So I will leave it to you to read. And if you have questions, you can ask me. So basically, it's the figure on the left showing the 3 scenarios which I presented. Is the black is the normal distribution, and the solid black is in bias distribution. And then if you turn on the forward pressure, you get the green. So that is how the probability analysis will come in to play a role, because it is affecting the factor of safety of 1. So meaning the fact that the probability of failure is mostly affected. The last slide on conclusion, please. So for the conclusion remark, so I would just make a few points. So use of the PSPA approach can reduce the epistemic uncertainties when dealing with seismic hazard, including both the interface M9 earthquake and the non-interface M7 earthquake. And in the lower mainland, I would suggest not to use the UHS directly from the GSC model. Instead, I would recommend for the design of 1 in 2475-year ground motions, you use the source-specific structure for 1 in 5,000 years for both the interface M9 earthquake and also for the non-interface M7 earthquake. After that, we developed the ground motions for those 2 types of earthquakes, and then do the site response analysis or dynamic analysis using those ground motions for this 1 in 5,000 year individual spectrum. After that, you can look at the 2 sets of results and do, if they are close enough, you can do the design using those results and picking the high one. If they are far apart, then you will need to refine your analysis. That is on PSPA. Regarding the probability-based analysis, this is the first part of the study which I'm working on. It's mainly for risk analysis purpose, and that could be embedded in the risk analysis. There's still more work to be done, including the analysis for subduction interface earthquake, and also for other levels of ground motion response spectrum. That is my presentation. Thank you, Shane, and everyone, thank you.
Thank you very much, Dr. Wu. If anybody has questions, feel free to reach out to Dr. Wu online via the private chat.